Thank you for everyone who joined us here on time for today's Veolia Water Tech Talk. My name is TJ Willits with Veolia Water Technologies, and I'll be your moderator for today's technical presentation. I'm just looking at the login here, and it looks like people are still trickling in. So we're going to give them a few more moments to get settled and take care of any technical issues they may have before we go ahead and kick this webinar off. So thanks again for joining us. Hang on, and we'll start in just a few moments. We had several people just log in here and still some people in the waiting room. So just hang tight and we're going to start the webinar in just a few moments. Thank you. Okay, we're going to get started. Again, my name is TJ Willits with Veolia Water Technologies. Thank you so much for joining us for today's presentation, Cooling System Control, Mission Critical Water Treatment Practices. We have a lot to cover today, so we're going to hop right in and get started. Just some technical points here. You should be hearing me speak now. There's two options for audio. You could log in either through the computer and listen through your headphones or speakers. If you're having issues with that, you could use your telephone and switch to that mode and dial in, and you could hear listening over your cell phone. Also, your microphone is automatically muted, so you won't be able to speak, so you don't have to worry about muting yourself there. But no worries, we have a question and answer panel on the right side of your screen. At any time throughout the presentation, go ahead and type your question, and then we will try to get to as many of those inquiries after the main presentation today. If you weren't aware, Veolia Water Technologies has a program, the Tech Talks program, and this webinar is part of that program, but we also have several additional webinars being added here in the near future. You can see some of those listed on there. We have one for the pharmaceutical industry coming up, and a series of digital webinars as well. So be on the look at our website, veoliawatertech.com, and be able to sign in for those webinars in the future. We also have a on-demand webinar on our library, on our website. Go ahead and log to our website and you could access 40 or 50 webinars that we keep track on there and update frequently. And if you're with us today for the live broadcast, you're going to receive a PDF participation certificate that will usually show up in a day or two. So be on the lookout in your email or your spam folder to go ahead and download that PDF certificate when that comes in. Also, we have a short survey after the webinar that you'll be shown. Please just take a few moments to fill out that survey. It really helps us understand what's been beneficial about today's broadcast. There's also a place to log in there some ideas for future webinar content that you might want us to approach in future broadcasts. So take the moment to fill that out, and anyone that fills out that survey will be entered into a drawing and receive a Amazon gift card. So we'll have a little fun with that. And if you're new to understanding about Veolia Water Technologies, we're one of the world's leading water and wastewater treatment providers. We offer our services to our customers through technologies, a wide range of service offerings, as well as pairing together multiple technologies to do an integrated project. So that's a little bit about who we are as a company. And we serve a variety of markets, everything from mining, CPI, pharma, food and bev, oil and gas, and municipal, and many others as well. So we're very versatile in who we provide our technologies, service, and project supports to. And we're transitioning now to the technical presentation for today. With us are two water treatment professionals. Our first person that you'll hear from, his name is Ted Lawson. He's 40 years of experience in providing support and services to our clients. And you'll also be joined with Phil Mateo as well. He's an applications manager for Veolia Water Technology, specializing in providing support to many different customers in relation to their providing programs regarding water treatment for their utilities. So without further ado, I'd like to hand the webinar over to our first presenter. Ted, are you with us?
I am, TJ, and thank you for the introduction. If you could move to the next slide, thank you. To give everybody an idea of what we're going to be addressing over the next 30 to 45 minutes, we're going to start with a brief overview of the water that's used in cooling towers as makeup and gain a better understanding of the impact that water impurities can have on a cooling system. You might want to call that Water 101. And after we get a better understanding of water quality, then Phil is going to run through a more detailed review of the cooling system itself, how some of the various system components operate and rely upon the cooling system, and then the needs and methods of both mechanical and chemical treatment, and how you can ensure efficient water management through effective monitoring and control. Finally, we'll conclude with a brief discussion on water reuse related to its use in cooling systems, as it seems that the cooling tower is generally looked at as a default destination for reclaimed water in many industrial facilities. So let's begin with a few slides on the basics behind developing a relationship with this substance we call water and why it behooves us to understand it in our cooling systems. Water is pretty much an unappreciated commodity to many of us in the US, and historically, we have taken it for granted. In a lot of geographies that we serve here in the US, we have a reliable and seemingly endless supply. However, I think we've all seen over the past decade or so that we've begun to realize that it's not always the case. Not only is supply limited and becoming more costly to obtain, but in many cases, the quality of the water that we're getting is changing as well. So when we think of water, we need to realize that there's many different facets of this simple molecule that we refer to affectionately as H2O. First and foremost, where is the water coming from? Is it a surface water supply, such as a river or a lake, or is it well water? Does it come from your own plant's pretreatment or clarification system, or does it come from a local municipal POTW? Each of these sources has their own unique set of challenges associated with them, and you need to review these moving forward, and you'll get a little bit more on that in the future here in the webinar. Secondly, does the quality of the water remain consistent throughout the day, the month, the season, or even the year? Unmonitored and unexpected changes in water quality can really change the efficiency of your cooling system operation, and they need to be accounted for in the design of your control program. The most effective way to help your understanding of the quality of the water used in your plant is to obtain a water analysis. We cannot stress this enough. This should be done on at least a minimum of once a year, or more often if your water does have a history of changing its quality from time to time. So any changes in the quality of the water, or for that matter, any changes made in the operational parameters of your cooling system, can change the scaling potential, the corrosivity, the fouling nature, or the susceptibility of your system to microbiological growth. All of these factors form the basis for you, your management team, your water treatment consultant, and your staff to determine the best method of treatment and control that you need to exercise in your cooling system. So let's take a little time talking about this simple molecule called H2O. Sometimes referred to as the universal solvent, water has the ability, the unique ability, to solubilize the majority of the elements in the periodic table. So this makes this simple liquid very complex in its performance characteristics. Very difficult to understand without an analysis, and potentially very dangerous if not treated and controlled well in your systems. And today we're speaking specifically of the cooling systems. I've got some of the more common impurities listed on this slide here, along with some pictures of potential problems that may present themselves in your system if it gets out of control. On the left, I mentioned the hardness impurities, calcium, iron and magnesium. They can precipitate out of solution in very high heat areas such as exchangers, condensers, reactors, etc., and form energy robbing deposits such as shown in both the lower left-hand corner photograph and in the upper right-hand corner. Anionic impurities such as sulfates, chlorides, carbonates, bicarbonates, alkalinity can all contribute to these scaling issues by helping to form less soluble complexes that will only add to the deposit potential if, again, left uncontrolled and move beyond the control parameters you have set up. Water can also become the vehicle for corrosion and corrosion byproducts in situations where dissimilar metals are present and facilitating the flow of electrons or metal loss from the anodes to the cathodes, as seen in a cutaway of a corroded valve stem in the upper left-hand corner. Dissolved gases such as oxygen, carbon dioxide can also complicate water efficiencies and alter water pH, which can influence the scaling or corrosive nature of the water, as well as contributing to accelerated pitting corrosion, which can burrow through standard piping and equipment very, very quickly. High dissolved solids will limit the water's efficiency by influencing how effectively you can cycle up or recirculate the water in your system. And also in excessive amounts, silica can also exceed solubility limits and leads to some very insulating deposits, which can threaten system operation and heat transfer efficiency. And lastly, we can't underestimate the presence of microbes or an environment that's conducive to microbial growth, because that can become both a corrosive and a fouling nightmare that can plague your system and its operation and create nightmares for your operators all year long. Don't forget, cooling water is a wet, warm, and due to the operation of the tower, typically a fluid that is loaded with organic nutrients, which foster microbial growth. So it's just water, right? Well, sort of, but it's certainly more than just the H2O when used as such in an industrial cooling system. Just a few other visuals to help you understand how water quality can impact your system. As mentioned before, hardness deposits can contribute very tenacious deposits in high heat flux equipment such as exchangers, condensers, chillers, production reactors, etc. This is due in part to what's called the inverse solubility of calcium. In other words, as temperature rises, calcium actually becomes less soluble in water, which makes it more commonly depositing on hot surfaces rather than on cold surfaces. Note the deposits on the upper left-hand photo. On the left side of that photo of a multi-pass exchanger, where the temperature is higher, you see more calcium being deposited in the tubes than you do on the right-hand side, where the water, inlet water, is of a cooler temperature. Cooling towers can also be impacted by the presence of organics and higher solids loading and begin to foam considerably. Obviously, the picture in the lower right-hand corner shows that. And that can be somewhat of a potential safety issue for your employees, as well as a supply issue with pumps that might begin to cavitate with foaming present. Lastly, corrosion and the presence of corrosion byproducts can lead to very aggressive equipment failures where equipment replacement is required. On the bottom left and the upper right-hand corner of the slide, you'll see a few pictures of microbiologically induced corrosion that occurred due to the presence of microbial masses under which were excreted corrosive byproducts. So with a little bit of a primer on various water impurities behind us, and let's not understate this, there's a lot more to be said when you look at a detailed analysis. I would encourage you to get to know your water and be prepared to address its use in your plant cooling systems, and make sure that your program for control and treatment is tailored to the water quality that you have. Now I'd like to turn the microphone over to Phil, who will begin a little bit of a deep dive into the operation of the cooling system and the many operational and control strategies used to keep them operating reliably and efficiently. Phil?
Thanks, Ted. So kind of an overview again of the operations. Today's cooling systems are highly engineered and very complex, with one change potentially impacting the entire system. If we were to follow a drop of water through the system, we'd see that it flows from a makeup water source such as the river, a well, a water reuse system into the recirculating water. It then passes through a heat exchanger of some sort, picking up heat, and then onto the cooling tower to reject that heat via evaporation. Then back to the heat exchanger to pick up more heat. To ensure that the cooling water accepts the heat from the heat exchanger, the exchanger surfaces must be free of deposits and microbiological growth. To demonstrate how dangerous these deposits can be, even a 1/16 inch of scale can decrease heat transfer by up to 50%. The heat exchanger is typically the most critical part of the cooling system as it usually touches the production areas of the plant. There are many types of heat exchangers, but the most common are some sort of form of a shell and tube or a plate and frame heat exchanger. An example of a shell and tube heat exchanger is in the top picture, and a plate and frame is on the bottom right, and a chiller that uses the shell and tube is on the bottom left. Regardless of the type of heat exchanger, they all work similarly. A hotter processed fluid, whether it's a water, an oil, a chemical, heat transfer fluid, whatever, a hotter processed fluid of some sort passes through the heat exchanger, transferring its heat through a thin metal heat exchange material into the cooling water. Both the processed fluid and the cooling water passes through the heat exchanger at specific flow rates, thus ensuring the desired heat transfer occurs as engineered. However, when that flow is disrupted or the heat exchange surfaces are fouled, the efficient transfer of heat is reduced, which may lead to the operational issues. It could lead to equipment failure and, of course, higher overall operating costs. A common but preventable problem is scaling of the heat exchange surface. This thin layer of insulating mineral scale, which is typically calcium carbonate, reduces the transfer of heat through the cooling water, leaving the processed fluid hotter than desired. This in turn again can lead to poor equipment performance, increased utility cost, and production downtime. A similar problem occurs when dirt or debris or microbiological growth plates out on the heat exchange surfaces. Lastly, any of the deposits or fouling could lead to under-deposit corrosion, as Ted mentioned, of the actual metal heat exchange surfaces itself, which leads to a future failure of the heat exchanger. Once the cooling water leaves the heat exchanger, it passes to the cooling tower distribution deck, where the bulk water is broken into smaller streams, typically via nozzles. This water then passes to the tower fill, where the water is broken down further into thin sheets, if it's a film type fill, or tiny droplets if it's a splash type fill, to increase the surface area of the water. Air is drawn or blown across this thin film of water, allowing it to evaporate. And with this evaporation, we get the heat rejection, leaving the cooling water cooler than it was when it left the heat exchanger. Typical cooling tower, we use an example of 10 degrees temperature drop from the top to the bottom. Each pound of water evaporated removes 1,000 BTUs of heat energy. This cooler water is then recirculated back to the heat exchanger to pick up more heat. In order for the cooling process to work efficiently, the flow across the distribution deck must be evenly balanced, and the nozzles, shown in the bottom left picture, must be in good working order and must be present. The distribution deck must be free of debris, as seen in the picture in the upper left, where there's a couple of boards that are laying underneath the water, causing the flow to change. The tower fill itself must be free of blockages, being debris, ice, anything else that would impair the ability of the air and water to flow as designed. And the picture in the top right shows a fouled and a clean thin film fill, and the lower right is a general schematic showing the airflow through a typical cooling tower. The recirc pumps that drive the cooling water through the heat exchanger and back to the cooling tower must be operating as designed in both flow and pressure. The system was engineered to reject a specific amount of heat energy. Newer systems try to utilize VFDs and other energy-saving equipment to reduce their electrical demand for electricity. The cooling tower fans must be maintained and operating correctly in order for the airflow to water ratio to be maintained. The fans can be gear driven or belt driven and consume a good portion of the electricity used by the cooling system. In many facilities, cooling systems are operated seasonally, especially comfort cooling systems such as buildings and hospitals and other air conditioning systems. Some have been idled as employees work from home or operations were shut down during the pandemic. As the spring arrives and as people return to work, these systems are brought back online and the tower is exposed to a heat load again. So, how do we set ourselves up for a successful cooling season? Remember, our ultimate goal is to promote efficient heat transfer and water conservation throughout the upcoming cooling season by eliminating the water-related problems. Again, scaling is the formation of deposits due to supersaturation of any dissolved solids in the water. Scales are commonly calcium carbonate, calcium sulfate, calcium phosphate, and various forms or combinations of iron. Corrosion is the return of the metals to their natural state, much like steel rusting in a yard in the rain. Corrosion requires the presence of oxygen, water, and a metal, which are all present in the cooling system. Fouling is the accumulation of unwanted material on the solid surfaces. The fouling materials can consist of either living organisms or non-living substances. Prior to restarting these cooling systems, though, proper maintenance of the equipment should be performed in order to ensure reliable operations through the season. This slide shows a very partial list of tasks that need to be conducted annually or prior to startup per the equipment manufacturer's instructions. These include the annual cleaning of the tower to remove dirt and debris, caulking of the tower seams and lubrication of the fan gearboxes, and preventive maintenance on the recirc pumps and other moving equipment. Again, follow the manufacturer's recommendations for best equipment reliability. Just as important as the need for maintenance on the tower and the heat exchangers is the need to inspect and maintain the chemical water treatment equipment. Chemical pumps should be serviced, fittings and tubing inspected and replaced as needed, fresh chemical ordered, and the chemical treatment program should be reviewed for needed changes and updates. This is also a perfect time for a good disinfection of the cooling system to kill existing microbial organisms, especially Legionella and other harmful bacteria. Lastly, it's also an excellent time for system-specific operator training, especially concerning Legionella exposure risk minimization for your employees. Later in the season, when some systems are idled or removed from service, a proper shutdown process is recommended. Some of the items are listed on this slide. Improper shutdown of the cooling system could lead to major issues when the equipment is next returned to operation. Of particular concern is microbiological growth, especially if the equipment was left full and wet during the off-season. Algae, slime-forming bacteria, Legionella, and other nasty organisms are likely present before shutdown, so removing or destroying these prior to shutdown is important. When possible, we recommend a complete draining of the system. A pre-draining passivation can be done to protect the metallurgy during the off-season. If the draining of the system is not feasible, the system should continue to be tested and treated, and flow should be periodically established to ensure passivation of metal surfaces is maintained. As we all know, maintaining efficiency in equipment operation equals cost savings. The savings can be in electricity, labor, and more importantly, avoidance of costly repairs and unscheduled production shutdowns. As we mentioned in previous slides, proper maintenance of the system equipment is key to maintaining operational efficiency and reliability. Developing a chemical treatment program that addresses scaling, corrosion, and fouling is key to preventing problems that cannot be engineered out of the system. As we stated earlier, this treatment program must be developed specific for that individual site, taking into account its unique makeup water source, cooling system equipment it supports, system metallurgies, flow rates, temperatures, volumes, and heat loads are all taken into account when developing the correct chemical treatment program. The operation of this chemical treatment program is equally important, so the equipment that supports this program must be maintained as well. This includes periodic calibration of pH sensors, rebuilding chemical pump heads, and replacing chemical tubing. Lastly, regular testing of the treated water to ensure the program is operating as designed is very important. A wonderfully engineered cooling system and its chemical treatment program is useless if the equipment fails due to a lack of regular testing and tweaking. One area where the chemical treatment program can impact efficiency and cost containment is the control of the cycles of concentration. In any cooling water system, we want to minimize the volume of water going to the sewer or wastewater systems, which corresponds directly to the purchase of fresh makeup water. These have costs associated with them, with sewer or wastewater costs typically being 2, 3, 4, even 5 times as much as the cost of the makeup water itself. And these costs will continue to climb as clean water becomes scarce. In an evaporative cooling system, such as these cooling towers, when water is evaporated, the dissolved solids are left behind in the remaining water. So over time, the cooling water gets more and more concentrated, up to the point that it can no longer keep the solids dissolved in the water. When this occurs, deposition occurs. This is the same reason you can only dissolve so much sugar in your sweet tea if you live in the South, as I do. Adding the sugar when the tea is hot is easier to do than when it's cold. This is an example of normal solubility. But many scales, such as calcium carbonate, are inversely soluble, meaning they fall out of solution and form a deposit in the hottest portions of the system, which would be your heat exchangers. So to prevent this, we only allow the water to get concentrated so far, and then we bleed off remaining solids to the drain. The ratio of dissolved solids in the concentrated tower water to the makeup water itself is called cycles of concentration. As you can see in the charts, by maximizing the cycles without oversaturating the dissolved solids, we can reduce our water and sewer usage and those associated costs. In this example here, by increasing the cycles from 2.2 to 3.5 cycles, the system saw a cost reduction of $40,000 in water and sewer. One thing to note, this does not include savings associated with less chemical needed to treat the system. But bear in mind, it's the treatment chemicals themselves that allow us to maximize these cycles without scaling and are typically a minor cost compared to the overall cost of operation. Some other factors impacting the maximum safe scale for the system are the types of dissolved solids in the makeup water, especially calcium and alkalinity. In this slide, we see how the differences in alkalinity and hardness in our makeup water affects the ability to achieve higher cycles due to their impact on the LSI. Now, LSI is a term in our industry which is a reference index used to determine the scaling or the corrosion tendency of a given water. It's calculated using calcium hardness, alkalinity, pH, total dissolved solids, and temperature. As the LSI increases and approaches 3, the water is considered to be scaling, while an LSI closer to 0 or less than 0 is considered to be corrosive. In the top graph, using well water with high hardness and alkalinity, the typical max LSI is hit after only 2 cycles of concentration. In the bottom graph, however, using surface water, such as a river, which is typically lower in hardness and alkalinity, the maximum LSI that can be achieved is 9 cycles. So this clearly shows how different makeup water sources can impact maximum safe cycles, which in turn impacts the ability to reduce water and sewer cost. In this example, we use the same well water as the makeup, but treat with and without sulfuric acid. In the top graph, using well water without acid, we're still capped at 2 cycles due to the LSI. That again is due to the higher alkalinity in the well water. However, the bottom graph, Using acid to neutralize some of the alkalinity, we safely operate at 10 or more cycles. Now, running 10 cycles is not practical, as you really don't save much more in the water, and you don't get rid of some of the built up solids. But the message is we can run higher cycles and still maintain a clean heat exchange surface. As we said earlier, when developing a chemical treatment program, we need to control scaling, corrosion, and fouling. And since microbiological growth can affect all three, we need to account for this as well. Again, scaling is the deposition of dissolved solids onto surfaces. Corrosion is the breakdown of metals to their natural state. And fouling is the buildup of other materials in the system. As you can see, we have our industry has a number of treatment families for each problem category and many options within each of these families. And we could spend days discussing the various molecules and where they are best applied. Selection of the scale control agents in the upper left, also known as antiscalants, is based on a number of factors, including the mineral content, water hardness, pH, alkalinity, and LSI. Environmental constraints and a company's internal policies may also impact anti-scalant selection. For example, in some areas, phosphate or even phosphorus in the outfall is regulated and not allowed. Corrosion control product selection is also pH and LSI dependent, but system metallurgy is very important. Most cooling systems have mild steel pipe with brass and bronze valves and copper heat exchangers. Some towers are galvanized, so picking the correct product for corrosion control based on the metallurgies in the system is important. Fouling can occur from dirt and debris, from corrosion byproducts, from dissolved solids, and from microbiological activity. Not only does fouling reduce flow through a pipe, it also provides a place for corrosion to occur and a place for Legionella to grow. The cooling tower itself acts like a giant air washer, so whatever is in the air will end up in the tower water. As we mentioned earlier, reducing the volume of water purchased as makeup, along with the corresponding reduction in water sent to the sewer, can reduce or at least contain operating costs associated with the cooling system. We at Veolia have an internal acronym called CORE, which is Conserve, Reclaim, and Reuse. We can conserve water by maximizing those cycles of concentration. This means less water sent to sewer and hence less makeup purchased. Repairing system leaks, keeping the tower distribution deck properly balanced, ensuring nozzles are clean and present are all ways to conserve water. Reuse can be an option where water is used again before disposal. Using cooling tower water bleed off or pump seal cooling is an example. Reclaim is an option that Veolia does a lot of, where other water used in the plant can be treated and then repurposed elsewhere. A good example is using RO concentrate as a cooling tower makeup source. If the RO feed water is softened, the concentrate can be sent to the cooling tower instead of the sewer. Or wastewater effluent can be cleaned up and used for boiler and cooling water makeup. And if you're a facility that's only metered on the city water coming into your facility and not your outfall, you should look into getting evaporation credits for the water that you've evaporated, as this evaporated water never went back to the city sewers, so they didn't incur any cost to treat it. Once a chemical treatment program has been engineered and implemented, keeping it running smoothly and correctly is extremely important. All treated systems should be tested periodically, typically at least once each day, probably more often for larger or more critical systems. Automation of a treatment program is relatively inexpensive versus additional headcount and is quite reliable. One innovation that continues to gain in popularity is the use of traced or tagged chemical products. Traced products incorporate a fluorescing molecule in the blended chemical product. Tagged products incorporate a special molecule in the backbone of the chemical molecule itself. These products can then be monitored automatically using sensor technology ensuring 24/7 measurement versus one measurement a day. Once the program is up and running correctly, periodic performance monitoring is important. This includes review of trend data over time, use of 60 and 90-day corrosion coupons, etc. This allows you to gauge your progress versus your KPIs. So, manual logging of data in a notebook has been replaced by electronic log sheets and the power that data brings with it. As mentioned earlier, chemical treatment programs need automated monitoring and control to work their best. Today's operators are stretched thin. They're asked to do more with less, so having automation that can watch the chemical program when the operator is doing other things is important. There's numerous manufacturers of simple standalone microprocessor-based feed and control equipment for our industry. In addition, Veolia has developed our own line of PLC-based automation systems using Allen Bradley equipment, with currently 4 standard cooling water versions, 3 boiler, and a bunch of customized wastewater versions. The cooling automation packages does use digital sensor technology and multiple sensors for traced and tagged chemistry. While the controllers give us great flexibility in choosing the right feed and control methodology based on the specific client needs, the real power is in the connectivity capabilities. These controllers can be remotely linked to an electronic data management tool such as Vision NA, as well as our digital services platform Hubgrade. Remote access and alarming capability allows for quick reaction and program changes before damage can be done. And the data management allows us to trend the data, find root causes of problems, and implement countermeasures to ensure these events don't repeat themselves. With the explosion of internet-based services, Veolia has developed our own digital services offering called Hubgrade. The Hubgrade platform allows our clients and our staff to remotely monitor and in some cases control systems automatically. Hubgrade is built on 3 pillars. First pillar is essential, which is the data collection and management portion with access to current and past information for both the client and for our Veolia support personnel. The client portal is accessible anytime, from anywhere, on any device to include your smartphone. Performance is cloud-based automated control for specific equipment, such as ROs, clarifiers, and other equipment. The software receives data automatically in the cloud, compares it to the specs, and implements needed corrections. An example would be the automatic backwashing of filters or cleaning of membranes when needed, ensuring that the equipment operates at peak performance levels. Assist is the third portion, and this is a live support service package for critical equipment where Veolia can monitor and troubleshoot systems live and then proactively advise our clients on recommended solutions. Now, while not all services are needed everywhere, the collection and review of data is critical to ensuring equipment uptime and efficiency. So, beyond the chemical treatment, there's a number of mechanical devices that we recommend that can greatly improve the operation of a cooling system. As we mentioned, a cooling tower acts much like a giant air washer, drawing in huge volumes of outside air. So anything in that air will end up in the tower. Anyone who has ever had a plant operating next to a large farm operation has seen what that cooling tower can suck in, especially during spring tilling and planting. Side stream filtration reduces suspended solids and debris in the system cooling water, which leads to less fouling of the system. The picture on the lower left shows a continuously self-cleaning disc filter. The middle shows a typical multimedia filter, and on the right, a smaller cartridge filter. Decreasing suspended solids can also help reduce microbiological growth in the system because suspended solids can be a good source of food for microbiological organisms. Again, if you're located next to a farmer's field, you already know that. Every time they fertilize their fields, the tower gets green. Decreasing biological growth, in turn, helps to reduce the biologically influenced corrosion. And in addition, scaling can be reduced with side stream filtration by limiting fouling and corrosion byproducts, which can also contribute to scale formation on the heat exchange surfaces. Effectively managing these conditions through filtration can optimize system performance, often resulting in moderate to significant energy and water savings. Microbiological growth in a cooling system occurs naturally and it should not be feared. The system provides everything microbes need to thrive: oxygen, or in some cases, sulfates, food, warmth, and sunlight. And while this is perfectly natural, their presence can lead to problems in our systems if not controlled. The study of microorganisms in a cooling system could keep a microbiologist busy all day. Luckily, our industry has become quite proficient in the identification and treatment of the microbes most commonly found in open cooling systems. And in general, they fall into some major categories such as algae, yeast, bacteria, fungus. Bacteria is probably the biggest, along with algae. The algae in the cooling tower will definitely disrupt the formation of that thin film of water inside that tower fill, which then reduces evaporation. But they also allow for the growth of other microbes such as Legionella, slime-producing bacteria, and sulfate-reducing bacteria. And the algae mats eventually can slough off the tower fill and flow through the recirc water to the heat exchanger, either plugging it or baking onto the heat exchange surfaces. This, of course, leads to the poor heat transfer and then can lead to underdeposit corrosion. Certain bacteria can wreak havoc on the cooling system. Slime producers secrete biofilm that captures debris floating by, leading to poor water flow, deposition, and corrosion. Sulfate-reducing bacteria can hide in the dark portions of the cooling system, and they use sulfate in place of air for oxygen and secrete acidic sulfides into the biofilm, which corrodes the metal surfaces that they're affixed to. And lastly, any biomass in the water becomes a breeding ground for Legionella. So, how do we control microbes in the system? What we use is called biocides or microbiocides. So, generally speaking, we classify microbiocides as either oxidizers or non-oxidizers. Microbiocides used commercially must be EPA registered and approved, and must be approved for use in the states where they are used. That's very important. And more importantly, they must be used as approved. So ensuring that chemicals that are used for one function aren't brought to the cooling tower and used as a biocide is important. As we said, the microbiological growth can lead to scaling by providing a seed site for crystal growth, corrosion by secretion of acidic byproducts, and fouling of the growth by their colonies and or mats. So, an oxidizer is a biocide that will kill by burning the cell wall of a microorganism. The microbes cannot develop an immunity to oxidizers, but they can tolerate some oxidizers if the dosage rate is too low. Examples of oxidizers are sodium hypochlorite, commonly called bleach, bromine, peracetic acid, hydantoin tablets, etc. They're usually fed to maintain a residual in the water. Non-oxidizers operate differently, and they kill through a mechanism that's known as poisoning. Each works in its own way. Some kill by disrupting the cell wall, others by interfering with the metabolic pathways, and still others by impacting reproduction processes. Some microbes can develop an immunity to certain non-oxidizers over time, so alternating two different non-oxidizing biocides is typical. Regardless of the biocide chosen, they are all at the mercy of time and dosage. In other words, they must have a minimum concentration for a minimum contact time to fully work. And one thing to note, since microbes are present in every water, their presence alone is not a cause for fear. Their uncontrolled growth is the problem in our cooling system, so we seek to control microorganisms. Sterilizing a cooling system open to the atmosphere and operating as a large air washer just isn't practical, nor is it necessary. As of late, a lot of information has been shared about Legionella, and it is one of the more common bacteria found in cooling water. It's the bacterium that causes Legionnaire's disease. Now, this bacteria can be found in most untreated waters in the world, to include streams and lakes and rivers and even the mud puddle near your house. It also lives in cooling water for the same reason the other microbes survive. This bacteria does, however, pose a risk to humans that inhale water droplets containing Legionella. So individuals with compromised health, weakened immune systems may contract legionellosis, a type of pneumonia, or Pontiac fever, which is a little bit less harmful illness. But for some folks, legionellosis can be fatal. Since the cooling towers intentionally create little droplets of water as the water cascades down the tower, plus fans push or pull large quantities of air through that water, a tower with Legionella may have aerosol with Legionella in it, and those droplets can be breathed in by personnel working in and around the tower or downwind. So this bacteria is not particularly strong, so proper treatment of the cooling water system with biocides will control Legionella as it controls the other microbes. However, due to the dangers associated with Legionella, various trade groups and the CDC have written best practice manuals with legislation likely to follow, outlining various steps that tower operators should take to minimize their risk to humans. Of note, the testing for Legionella is fairly inexpensive and readily available. We recommend testing quarterly in order to ensure this bacteria is under control, and it also helps reduce liabilities for the owner. Until specific laws are enacted, and they will be enacted at some point, various industry groups have written recommendations to help guide us in minimizing the risk of Legionella. The American Society for Heating, Refrigeration, and Air Conditioning Engineers, commonly known as ASHRAE, has developed their standard known as ASHRAE 188, published in 2018. It is currently the best known and followed set of recommendations for risk minimization here in the US. It was written with the help of various industry experts and with the help of the CDC. It outlines steps that cooling system owners should follow, from site design all the way through to regular maintenance and testing. Its recommendations are specific for commercial and healthcare building systems, but it's very appropriate for for industrial and manufacturing sites as well. I did confirm this with an attorney at a trade show one time who deals with this as his exclusive business. Its biggest recommendation is to have a written plan for risk minimization and then follow that plan. This is often called the water management plan and has led to a cottage industry of professional water management plan writers and consultants. Ted?
Thanks, Phil. And my gosh, what a litany of information. I'm sitting here jotting down ideas for possible future webinars. And I guess I would encourage everyone to take TJ up on his offer and send in any requests or any ideas that you might have where you would like to see more information on certain facets or portions of what Phil has been reviewing here for the past 30 minutes. So let's switch gears a little bit to address something that we see happening more and more these days. As reliable sources of fresh water become harder to find and more expensive to obtain, sometimes a solution can be found within the property lines of your site by simply looking for water streams that can be reclaimed or recycled before leaving the facility. And since one of the largest water using processes in many industrial facilities are the cooling systems, many of our customers are taking reclaimed or recycled water back into the plant and using it as cooling tower makeup. While this can have a positive impact on your overall water footprint and look environmentally or socially acceptable, it might not be as straightforward as you think. On this slide, you can see just a general checklist of questions that we typically ask clients who are considering implementing a water reclaim or recycle strategy. Obviously, each customer situation has different drivers behind it, and the systems that we investigate each have their own unique operational aspects. But As you read through this list, you'll see that we need to consider where the reclaimed or recycled water is not only coming from, but where it's going to be used. And we hope that you've learned today that putting the wrong quality water, improperly treated or improperly controlled into the wrong application can have a devastating effect and impact on your plant. If you don't have a clear-cut destination for reclaimed water, just please be sure that your company is not viewing the cooling system as a default dumping ground for reclaimed water to fully or simply fulfill their sustainability obligations or objectives. It's not always quite that simple. So taking these thoughts forward and focusing on the cooling tower system itself, again, it's not always a slam dunk solution that it appears to be if you don't understand the details of these systems and their operations. So before you blindly start dumping reclaimed water into the cooling tower as an alternative source of makeup, here's a more detailed list of questions that you need to be aware of and consider related to these situations. As you can see from the list, many of the questions are similar to those on the previous slide and in the previous portions of the webinar, where we were discussing water quality, control limits, and other operational factors of the cooling system. Remember, if the makeup quality of the cooling system changes, all of the treatment and control parameters need to be adjusted accordingly. If not, a cooling system can quickly spiral out of control, and all the value of what you were hoping to receive by introducing reclaimed water will not be achieved. Most companies these days look at water recycle as the right thing to do from a sustainability perspective. But unless the economic drivers and the management support exists across your organization, it can sometimes be an uphill battle to prove that the initiative has both economic and operational value. Let's take an example. You're working in a food manufacturing plant and you're trying to reduce your overall water footprint. You conduct a study, you do some calculations, you determine that you can save both energy and water by recovering condensate off a process exchanger or evaporator. The energy savings is a no-brainer. Simply run that stream through a heat exchanger and watch the BTU savings start to accumulate. But then what do you have left? You have a cooled down condensate stream that you want to now use as cooling tower makeup. What's its quality? It should be pretty clean, right? I mean, as a matter of fact, it should be pretty close to distilled water quality. Maybe it could be, but maybe it's not. It still can impact your tower's water treatment, either positively or negatively, depending upon how you adjust. The stream could still contain volatile organics that could present food sources for microbes where you need to adjust your microbiocide feed. That needs to be understood and accounted for. Also, by nature, condensate is low in hardness, alkalinity, and dissolved solids. So it's going to be very much less buffered, could contribute to a lower pH, and typically create a more corrosive makeup water quality than possibly beforehand, where your water may have more of a scaling tendency. So while this near pure water quality can have benefits in allowing for greater cycles of concentration in your cooling system and reduce the need for freshwater makeup, it can also be threatening if its quality is not understood and the chemical treatment program and system operational parameters are not adjusted accordingly. In these situations, it's more critical than ever that you monitor and control water quality even more stringently and also have in place a process equipment monitoring program, as Phil talked about earlier, and make sure that the key system components in your cooling loop are being adequately protected and continue to operate both reliably and efficiently. So I don't mean to scare anybody away from using reclaimed water as a cheap source of makeup. You won't find a bigger proponent of reclaiming and recycling water than yours truly. Properly planned for and managed, this is a real opportunity for cost savings and overall sustainability and water footprint reductions by implementing this type of initiative. But no surprises here. Just to recap, we need to make sure that the quality of that newfound alternative makeup is consistent and reliable. Again, remember earlier we talked about having a water analysis. Number two, we need to understand the nature of the water. Does it have a scaling, a fouling, or a corrosive tendency? And how does that change its operation in your cooling system? How does it affect bleed rates? How does it affect flow requirements? How does it affect the chemistry portion of your treatment program? And lastly, what changes need to be made in the monitoring, feed, and control parameters to reduce risk and make the changes sustainable? One system and one approach that we've found very successful in not only reducing cooling system makeup requirements, but in eliminating bleed discharge is Veolia's Zero Liquid Bleed System, or as we call it, ZLB. This trademark technology minimizes water-related problems by first allowing you to close the bleed valve and allow system impurities to cycle up 50, 70 times, and in a few cases, we've even reached 100 cycles of concentration. We do so by minimizing scale and deposit control by achieving less than 30 ppm of system hardness in the recirculating water. We also do so by controlling corrosion through the utilization of cycled up silica levels in the cooling water as a natural corrosion inhibitor. And lastly, biological fouling is controlled by maintaining the recirculating cooling water in a biostatic pH range, which minimizes the growth and aggressiveness of most major biological strains. The ZLB system is not designed for every cooling system, but where there are minimal uncontrolled losses and where the water can be cycled up effectively to fit within the desired operating window for ZLB, it may be an excellent fit for your system. So if anyone's interested in learning more about this, we'd be more than happy to talk to you about it offline. But our ZLB system does help us in many areas in this regard. So if you do believe there are opportunities for using recycled water in your cooling system, please make sure that you can prove that the gains outweigh the pains. And by that, I caution you to remember that each system is different. We recommend 4 simple steps be taken to evaluate the benefits of recycled water in use as a new source of cooling tower makeup. First and foremost, conduct a thorough system audit and understand the use of the cooling water, the equipment that uses the cooling water, how it exchanges heat, whether it's operating properly under the current conditions, how it's performing across the entire system, and any areas of concern that you need to be aware of if the cooling water quality has changed. Number 2, work with your water treatment partners to develop a plan and also utilize an integrated approach, which includes chemistry, equipment, technologies, and services to modify or redevelop a new system operational plan for use of that alternate supply of water. Remember to take the blinders off, get creative, but be prepared to validate your recommendations or changes that you want to try to make. Number 3, management support is needed because there may be a need for budget monies or resources outside of your area of responsibility. As well, management approval is going to be needed to sign off on the ROI for the project. Without this, we see most recycle programs falling flat because their long-term fate could be in jeopardy without that economic justification. Therefore, it's critical, looking at the diagram on the right-hand side of the slide, to understand the total cost of water. Water has many costs beyond just the price paid to buy and dispose of it. That said, when these 2 costs alone total more than $5 to $6 per 1,000 gallons, reclaim and recycle becomes much more attractive in most industrial facilities. But to bolster your efforts and to justify the cause, also remember to take into consideration the costs associated with the impact of the water usage in the plant, operationally, financially, environmentally, and socially. What happens to plant production and product sales if water issues threaten to shut down a process? What happens to your plant's reputation and image if there are water-related discharge issues? These and many, many more are real costs that need to be factored into the total cost of water. And don't forget to use a straightforward scientific method in your efforts. Try and change as few variables at a time so that you can monitor the impact of your changes as they take place. And lastly, because we all live in a competitive industrial climate, and as your finance department will be quick to remind you, cash is always king. So please be prepared to develop and fight for the ROI of any reclaim or reuse project that you initiate using cooling tower water makeup as a source. But if the stars are all aligned and you do have a true opportunity to take advantage of, but you're not sure what to do with the quality of the water being offered up to you as the new alternative makeup source, rest assured that we have the technologies and services needed to help you transform your newfound water quality to whatever you need it to be for use in your plant's cooling system. For example, if your water is high in suspended solids, there are filtration technologies available to reduce solids down to as low as 10 microns, even removing particles such as some bacteria and viruses. If the mineral content of your water needs to be changed to control scaling potential, both cationic and anionic impurities can be removed through either full flow or partial flow using standard ion exchange or membrane technologies. If organics are a problem, both aerobic and anaerobic digestion technologies can help to remove these organics and create excellent quality water suitable for use in a cooling system, and again, doing so by removing disposable waste volume in the sludge that's generated. If you think simply that you're going to be forced to reduce the cycles of concentration in your cooling system because of a poorer quality makeup, as Phil outlined earlier with his LSI calculations and graphs, you might need to explore different water treatment chemistries that might help you extend the use of the water in the system without further investment. These decisions are based on whatever limiting factors exist in that new makeup water quality source. And if you want to eliminate bleed entirely, as we discussed previously, our ZLB system might be one option for that. Or you need to send the bleed back through an RO and or to an evaporator to recover the last remaining volumes of water while minimizing waste disposal volumes. So in closing, I just want to emphasize that when it comes to water reclaim in a cooling tower, and in particular, used as an alternative makeup source, every situation is going to be different. There's no across-the-board solution, and plans need to be developed for each individual system using an integrated approach, combining chemistry, equipment technologies, and services to help you develop whatever program suits your operational needs in the plant that your cooling system is serving. Develop a total cost of water approach and use this as your route to establishing the cost justification for this change in makeup water quality. Be confident that you're taking the right approach, because it can be and it should be, but also be prepared to justify the true cost advantages of this change in order to prove that the approach is truly sustainable. So as we outlined in slide 1 of the webinar, we tried to put together a webinar content that established that encompassed all aspects of a cooling system and its operation. In the process, we have gone through a boatload of information that we just scratched the surface on. First, we talked a little bit about knowing your water or the water quality. Understand it and the levels and types of impurities in it. Does it have a scaling tendency or a corrosive nature? Is your current chemical treatment program set up to specifically tailor to the tendencies of your water quality? Do you have in place an effective monitoring and control program that you can ensure the program is effectively implemented to provide the results that you and your production processes need? Secondly, we reviewed many of the aspects of proper operation of a cooling system including proper startup and shutdown procedures, key operational heat exchange equipment, and many of the operational guidelines necessary to keep your system running reliably and efficiently. And then we lastly spoke about how critical it is to not just have in place a chemical treatment program, but equally as important to make sure that you implement a proper monitoring and control program that can give you the insight needed to stay on top of the system performance. And finally, we spoke briefly about the alternative makeup sources that are available for cooling tower operators. We reviewed the benefits and potential challenges of changing the quality of the water in the cooling system. While providing a home for reclaimed or recycled water, a well laid out plan and control strategy must be developed to ensure that you're not endangering system integrity, the reliability, or the efficiency by introducing a different quality makeup. So with that, I'm going to turn the session back over to TJ, who will open up the Q&A session. Thank you so much for your attention. And please feel free to reach out to Phil, myself, and or TJ to follow up with you on specific topics or questions that you might have. TJ?
Thanks so much, Phil and Ted, for that deep dive into this particular subject. It was really great. We probably could have scheduled a series of webinars on this to cover it in more depth, but we appreciate that. Thanks for the few people that put their questions in the question box. We're going to get to as many as we can today. We'll probably have time for one or two, but we'll follow up via email on any questions that we can't get to. But one of the questions I just want to kick off with is just for Phil is how can you check the extent of corrosion that's happening within a pipeline within a cooling system?
The typical standards for doing this follows ASTM, and the process can be using corrosion coupons, which are sacrificial pieces of metal that are put in the water line under a flow rate that represents the flow rate through the pipe, and that metallurgy would match the metallurgy in your system. So typically copper, mild steel, stainless steel, it could be whatever. And you leave them in there for 60 or 90 days, and then you weigh them again, and it will give you a mils per year corrosion rate. And then you compare that to the industry standard. Another way to do it is to use corrators, which are an electronic device that uses a sacrificial tip that will corrode away, and you can instantly know what your corrosion rate is. And then for heat exchangers and stuff, especially shell and tube, there are folks that'll come on out and do testing of the thickness of the heat exchange tubes themselves. There's a whole industry for testing that to see how thin the walls are of the heat exchangers themselves.
Great, and I want to let people go on to the next meeting they have for their day, so we're going to wrap up now. Just a reminder, if you, upon exit, if you could take that survey, it would be really great to help us on future webinars and also learn about the quality of this webinar presentation. And other than that, if you need anything else, please visit our website, look at our other webinars, or browse our on-demand library of webinars. That would be great. And it's at veoliawatertech.com. I'd like to thank both of our presenters, our panelists for today, to provide all of that expert experience, information. And also like to thank every one of you who spent about an hour of your day to learn a little bit more about this really important topic for your facility. So again, thank you, and I wish everyone a wonderful week.